Which is the need.
Do you want me to solve exercise now? Or somebody else can solve?
Let them. Yeah. Now they were with exercise 1. So let. So easy is term is relative.
So the same.
It is a relative term. Relative. Relative. It is the body of not copy. Think about requirement.
And look at the exercise. It helps you to sweat as well.
Correct 12 वाला. Correct. See.
Saw something?
Getting this.
Which one? Yes. Okay, I saw for you tell. But you were very sorry. Sorry. Because it's so beautiful. She saw for you tell? This is the best exercise. Maybe it's the only one I can solve. Okay. Tell me what is exercise 12. No snack is Hamiltonian. Okay, this is the problem. Proof. I have a condition. Suppose, let's use some other color. Suppose G is a Hamiltonian stack. What is this Hamiltonian graph? Sorry. What must be a graph Hamiltonian? Let's do it. So we have something like this. How many vertices we have? Even. And then there are no edges. We have also edges inside, yes? 1, 2. Do I have even number of vertices? Yes. Let's say I have something like that. But this outer cycle is even, yes? So we have brown color. Let's put it every second. Do you see now the proof? Do you see the proof? So on the Hamiltonian cycle, I will consecutively color the edges brown, red, brown, red, brown, red. It's coloring. Whereas inside the one factor outside, I will leave it green. Now you're sorry that you didn't do it, yeah? Okay, next exercise which I recommend is this was 12, exercise 13. It says you have Blanchet snarks, so you have to take two Peterson graphs and use dot products. You can use dot product in two different ways and you can get both Blanchet snarks. Let's do that. Okay, exercise 13. We can exercise 13. Look, this is the Blanchet snarks, yes? And where's the dot product? This is dot product. Take two copies of Peterson graph. Make dot product, you will definitely get one of these two. Then make a product a little bit differently, choose some edges, you will get the second one. This should be a little bit drawing, but you will do it. The 12 was easier, you don't have to draw much. Okay? Come on, you should do it. Exercise 13. Yes? Maybe we should, we can't do it. Try exercise 13. It's very easy. We have a similar one. The time is very old. And you have another one. I also have sorry, this is also yours. I also have this is the same, but 60. And I have but if you really want to work, I could have you have the big one because this one is 60. It's like this. You need one screen with the principle. But I was looking at it's out of the so I'm going to say $50 and we will need some nice. But this is all. This is like $2.
I think yes. Okay, anybody something?
Anybody else out? Okay. Yeah, you were.
So we have to use the files to do one glass, yes. Oh, yeah.
Yeah.
the first day lecture material is here. But you will send the PDF if somebody wants. Because I'm going to dispose it today, so you can take, somebody wants to take it. Original ones. Yeah,
So here we have two copies of Peterson graph. According to the dot product rule, I will remove two vertex of the I guess right Peterson graph. Let's say this one. These three vertex will go away, and let's say this vertex. So we have four vertex that are yet to be saturated. And in the second Peterson graph, I will remove two edges. So let's say this one and say this one, and I will just connect them. So this with this, this with this, this with this, and this with this. Yes, just the construction.
Other colors.
So which is this graph? The first one or the second one?
I think this is the first one.
So what about the second one? So what edges you choose here? So you choose here you move it. So here you remove it to vertices, yes?
Yes.
And then you choose here two edges and you remove the edges like this.
Yeah.
Can you choose these two edges in some other way? When you use in some other way, then you will need the second one. Because Peterson graph is edge transitive, arc transitive, vertex transitive. Here you remove two adjacent vertices. Which one you choose to adjacent doesn't matter. Because you have no freedom. But here, maybe when you take no incident to edges, maybe you have more freedom. Can you maybe draw the Peterson graph? Can you draw up, draw down again Peterson graph? And let's try to choose two non-adjacent edges in two different ways. Can we do that or not? Yeah. But let's see it just. So now first, one way to choose is that this make it red and this make it red.
This
And let's say this one. So these two edges, okay, have only common. Can we choose it in some other way? Maybe make it this yellow. I think you can green, take it green. Choose this green and get green. You see? These two edges, the red one on distance one. There is edge between them connected. And these two green are not on distance one. There is no edges directly connecting them, yes? I don't see it. They are on distance two. So before you use this, yes? I don't know that. Now try the same operation by choosing such edges. Yes. This is a little bit easier. You listen to them and then ask some questions. Listen.
And this should be the second graph. Maybe it's a little bit essentially more artistic written, I don't have. I think that's what we Sorry? The second one. Yeah, two ways on to say two ways. Anybody saw maybe what is that? Do we have solved any other question or I have it? I know I have it. I also really use this exercise 3. I like such problems to solve without much writing. Even less than exercise 12.
Exercise 3.
Exercise 3 should be very easy. One-line proof. Exercise 3 is one-line proof. Half-line. One-third. Exercise 3 is very easy. One-line proof. Half-line. One-third. Exercise 4, also half-line proof. So you can prove in one line, exercise 3 and exercise 4.
That's what they're done. He's thinking something but not confident.
Sorry? Are you sure?
Not sure. Yeah, it's up. And then,
Yeah,
let's see.
yeah, that's half line.
Half line.
Otherwise doesn't count.
Yeah. Half line, yeah. Half line, you are not writing, right?
Right, just one. Maybe you will have to go to school, yes.
So, half line here.
You're out of space. Yeah, okay. Number 27, good start. It's killing, yes?
NK by 2. And what about the degree of the graph? It equals to k. So we want to show that it is simply not k edge colorable, right? So we are done. So suppose we are able to do it with k colors, and for doing it with k colors, all the edges are colored. That means one color class should contain how much edges? That floor of this n by 2. Okay, but if you multiply this with k, and that will be strictly less than nk by 2. So all the edges might not be covered, I guess, in that
This is
way.
the half line which I wanted, yeah.
Oh.
Okay, try now the next question. What's the next question? Where is the next question? Give it to him. Yes. It's very similar. Give your free space. Half line. Exercise 2, exercise 3 now, yes.
4, right? Even number.
In very similar fashion.
यहाँ बैठ करके थोड़ा so that is it. And edges is subdivide means and edges is subdivide. All edges are just one edge is subdivided.
subdivide
Only one edge.
yeah.
One edge. इवन ऑर्डर सब डिवाइड कर दिए तो ऑड ऑर्डर हो गया, बट इस बार उसका डिग्री 2 हो गया, राइट? रेगुलर नहीं हुआ बट डिग्री 2 हो गया.
It's easier.
No, no.
Similar way.
No.
Because okay, your arms. Each of degree K is one vertex. Yes. Yes. If you want, sorry. Can I just number of edges in K plus 2 by 2.
Anybody else? Can
Which one?
I'm just trying. So I need question. So suppose we have a graph G, something here and some here. It's a regular graph. So suppose this is delta curl regular. We make a point, let's say V here. Initially it is delta curl regular, so let's C1 is assigned here to this edge. Okay. Other than C1, all colors are used here
and all are used here because we are using delta many color and all delta are used, right? So after making this new vertices V, we have only two possibilities. Either we assign C1 to the lower one or the upper one. So if we assign C1 to the lower one, we need extra color to color the above one, right? Not getting my point? Delta colorable. So what we need to prove is delta plus 1 colorable, right? So I am using its delta colorable, and then for delta plus 1 also I will, if it is delta colorable, then also it is delta plus 1. If it is delta plus 1 colorable, then also it is delta plus 1. Okay? Right? Okay. So if it is delta colorable, then we got the result C1 is the lower one, then we need extra color C2 to color the whole vertices, right? No? Okay, let me explain a bit more. So initially I am thinking G is delta colorable. So I will prove after making a subdivision of one edge, we will get a delta plus 1 colorable class. Okay. So this is my graph. I am taking this edge E, and it is, since this is delta colorable, so C1 is assigned to this edge initially. Only C1 is missing in all the edges here and here. All other than C1, all colors are assigned to some vertices over these two right? Some edges over these two vertices. Now I have subdivided, I use some U here, and only I know the C1 is only missing to these two vertices, right? So either we have two choices, either we assign C1 to here or here. So if we assign C1 here, we need some extra color other than what we have available C2 to assign this the above one, right? And similarly in the other way, right? So, and if it is delta plus 1 colorable, then we know the maximum value is delta plus 1, right? So that's it.
Okay, what are the other exercises? This can be also very easy. Exercise 10. Exercise 10. You should find graph for which Shannon bound is smaller than Gaussian-Gupta bound. It's about 40 graphs. And then again one graph for which Gaussian-Gupta bound is smaller than Shannon bound. Come on, let's exercise 10. It's easy. There should be graphs. Otherwise, it makes no sense to have two bounds. If one is always smaller than the other. So have a look in Gaussian-Gupta bound and have a look in Shannon bound. We have delta with multiplicity and we have mean. Shannon bound is like 3/2 delta. Gupta and Gaussian delta plus mean. Exercise 10. It should be easy. Exercise 10, I recommend. We have two bounds. Take a look in Shannon bound, take a look in missing group bound. Find graph of each Shannon bound is smaller than missing group bound. Find.
Yes.
Okay? It's multi-graphs, yeah. It's about multi-graphs. Okay, please do it. The enabling problem is show the Peterson graph in the smallest time. You can time until tomorrow. Peterson graph with the smallest time. We must do that. Today no time, but if not, I do it tomorrow for you.
So here if I consider the maximum degree here is 7 and the value for mg is 6. So according to the Shannon bound, it will be less than equals to 3 by 2 into 7, which is nothing but 10. And according to Gupta's bound, this would be 7 plus 6, which is 13. So here the Shannon bound is better than the Gupta's bound. Now for the second one, where I have to show that I have to find a graph where Gupta's bound.
Don't write that much.
Sorry, sir. Is better than
Example bata.
Shannon bound. So the example would be here. My delta G would be 6 and mg is 2. Sorry, 3. No, yeah, it should be same. Yeah,
Not the same.
but this one is correct. K5, K11. So 10. Three by 2 into 10, 550. This and Gupta's bound. Here Gupta's bound is better than the Shannon's.
Let's go. Okay. Do we get some from the problem? Yes. 10 minutes. Which one should be easy? That one is easy.
Exercise 8. This symmetry graph is critical. Go to appendix at the end and test definition what means the equation graph is critical. So it is a graph of class 2, but whenever you move some edge, result a class of class 1. It means the edge, the curve will drop for 1, yes.
Sir, it is written that delta critical graph. So, age chromatic number delta or what? Just the chromatic number delta.
What's the question? Exercise 8. It should be easy. 2 lines. One for each item. Triangle the same, both will make critical graph.
He might sign a mountain.
You try and you
No, I'm asking the dad actually how can use the word age. Okay. Just 1 minute, sir.
Four lines.
Okay.
So much. But it's also not so good. Sure.
I didn't get this. But basically I am saying if du plus dv is less than or equal to delta minus 1, then I am able to show delta coloring of G, which is a contradiction because we have taken G to be delta critical. That means H geometric number, H geometric index is delta plus 1.
When you move this,
Yeah, basically let us say UV is an H and I remove E from G, then chromatic index decreases by 1. So it becomes delta, right? And suppose du plus dv is less than or equal to delta minus 1.
yeah,
Then at most delta minus 1 color will appear here.
yeah, around. And then
Yeah,
you put,
exactly. Then we have left one color and then we can color G with delta colors.
yeah.
Simple.
No, see, B, also B. Is that also B or not? You make a cut like this. You know that this, you give a cut like this, yeah? Then you remove some H here. This part you can color with less color. Then you remove some H here, this part you can color. Now you coloring for this part, you can color this part. Then put it together and each of the colors, you can color with less color.
Yes.
I'll explain them. And then get back to it.
Sir, I'm a little nervous actually.
Sorry.
Sir, I'm a little nervous.
Why to be nervous? It's we are only कौन explain करेगा अपन?
This way you kill the nervous. Take advantage of that. Take your mind. So, more than I have to be here. More than
Suppose T is a cut vertex, then we have at least one vertex in this side and one vertex in this side. Right? Like G1 is the graph. After deleting V, basically I am taking G1 to be like this part including V. Right? And since we are deleting at least one vertex from right side, so we are deleting at least one edge. Right? So basically this graph will be delta colorable, and also this graph will also be delta colorable. And how many edges can appear here? At most delta? No, in all, like G. Delta? Right. Suppose we can permute colors such that basically I wanted to say in left part only there will be at most delta minus 1 edges, and here as well delta minus 1 edges at most. In total delta edges. So basically we can permute colors such that we have to avoid at most delta minus 1 colors. So that is how we can extend that coloring to delta coloring of G. Okay. So basically I was saying, suppose G1 star be a graph containing G1 and V, and G2 star be the graph containing G2 and V, right? So G2 star is delta colorable and G1 star is delta colorable, right? Now we just need to extend that coloring to delta coloring of G. So in this coloring, what I can do, I can permute these colors such that set of the colors which are appearing here matches with set of colors which are appearing here, because these are like disjoint part now.
Should not match. It should not match. It should be different. And that we can do also.
Because we have delta colors. Sorry, I just yeah. So in that way we can just permute colors, and that is how we can we can extend coloring delta coloring of G.
That's it. That's okay, yes.
Okay. Yes. Okay. So tomorrow what time is lecture? 9, right? So 8:50 we here.